Alright guys, so I decided really quick to make a video for you guys just on the naming stuff. It's gonna be like I'm making it up as I go, so it might get a little scattered to places. But after that, let's go ahead and jump into it. So when you're naming stuff, first thing you want to pay attention to is it an ionic compound or a molecular compound? Easiest way to tell this um, is going to be, so you know the ladder on the periodic table where the metalloids are located? If it's to this side, it's going to be molecular. If it's to this side, it's going to be ionic. Oops. Whoa, what happened there? Ionic only has one I in the beginning, two I's total. Just so you know. Because I can't spell, doesn't mean you guys can. But alright, so ionic versus molecular. So ionic will have a metal, which is where this half comes in, and either a non-metal or it'll have a polyatomic. Another thing to pick up on too for ionic is if there is a polyatomic, then it's going to be an ionic one. Molecular is going to have no metals. So you can think of stuff like CO2. What's the name of that? Carbon di. We'll talk about that in a minute. Oxide. But you notice carbon and oxygen are both to the right. Whereas if you see something like this, NH4, let's go NH4 to SO4. So this is ammonium sulfate. This right here is the ammonium. And this is the sulfate. Most people don't have that much of a problem with the simple ionic compounds like this, NaCl. That should be one everybody knows, but let's go over it. That's sodium. So, wow, that was bad. So sodium, so you just take the name of the cation, which Na plus, Cl minus, and then you're going to take the root from the anion, which is, in this case, would be chlorine, so chlor is the root. You basically drop the I and E, and you're going to replace that with IDE, the ide. So just for practice, let's do another one, NaBr. That's going to be sodium. And then bromide. See, it's normally bromine, so IDE instead, so bromide. And then one more just for practice. Let's say I should have written some of these down. K2S. So the reason this has a 2 is because K plus, and then sulfur is 2 minus. Yeah, sulfur is 2 minus. So to make these neutral, you're going to need 2 potassium for every 1 sulfur. So K2S. I think she's more worried about you guys naming than balancing. But the balancing part isn't all that tough. It's just addition. So, okay, so potassium, right? That's the cation. And then sulf from sulfur, and then IDE, sulfide. And then for molecular, you have stuff like NO2 or CO. the Cl4. I'll go more into like how you can tell how to name these in a minute, but this would be carbon tetra, meaning 4, fluoride. This would be, of course, carbon monoxide, monoxide. And then this would be nitrogen dioxide. Again, we'll talk more about those in a minute, but let's pay more attention to our polyatomics for a second. So I know she showed you guys this right here, where this is going to be your parent group. So a good one to use for that would be chlorate. You know what chlorate is? Give me a second. It's ClO3 minus. So if I was to ask you what hypochlorite is, what would you think that would be? Well, if this is -1 oxygen, this is -2 oxygen. Oops, that should be, come on. And then this is +1 oxygen. So we're going from here down to here. So we're going to take away 2 oxygen. So we're going to have ClO minus. Likewise, if we were talking about chlorite, it's only -1 oxygen, so ClO2 minus. And then if we're talking about perchlorate, we're going to add 1 more oxygen to this, so ClO4 minus. You're going to see this a lot with the halogens, not the halogens themselves, I'm sorry, the polyatomics that contain halogens. So stuff like, let's see, BrO minus, BrO2 minus, BrO3 minus, BrO4 minus. So per, in this case, let's go ahead and switch colors, per bromate, then bromate, and then bromite, and hypobromite. You can see I did the same thing here, so that's from Br. Brom would fill in from here for chlorine, it's Cl, and that would be chlor. For F, fluorine would be FlUor, fluor, so like fluorate. For I, iode is what you're going to use, so like per iodate, iodate, iodite, hypoiodite. Like I said, you see it a lot more with the halogens than anywhere else, especially in the stuff that you guys will be naming. There's a couple other ones that it applies to. There's like, so if you're thinking of like sulfate, sulfate will be SO4 2 minus. So to go from sulfate to sulfite, what do you think sulfite is going to be? Well, if we look up here, when we go from 8 to ite, we -1 oxygen. So SO3 2 minus. Phosphate is PO4 3 minus. If we want phosphite, it's PO3 3 minus. The charge is going to stay the same. Make sure you remember that. So phosphate, phosphite. Trying to think of any other ones that you might come across that kind of follow that pattern. NO3 minus and NO2 minus. So this is going to be nitrate. Got a wild guess as to what this might be? Yeah, you're right. Nitrite. Well, if you guessed. If you didn't, then I think you knew it anyways. So let's see what else we have. We have something. Honestly, as far as I can remember, those are the main ones that you'll be messing with. Yeah, even looking at our list, those are the main ones. So that kind of covers that. I know I'm blowing through this, but I just want to cover stuff really quick to see if it'll help you out at least a little bit while you've been studying and while you continue to study. So coming over here to molecular stuff. So when we're talking about molecular compounds, we're going to use prefixes. And remember, molecular compounds are going to contain stuff that's on the right side of that staircase. So two nonmetals. So we can think of something like, oh gosh, N2O. So with this on the first one, you're going to use just the name. So I'm going to break this down for you. We're going to ignore numbers, and we'll use these as references. So ignoring numbers, we're going to talk about nitrogen. And then the cool thing is the second part follows the ionic naming. So ox, and then here you would drop the egen, and it would be ide. Just like before, you drop the n, you only use the root, and then you replace it with ide. So now we'll pay attention to the numbers. On this one, we have 2 nitrogens and only 1 oxygen. So I did not leave myself enough room, but if we have 2, that's going to be di. So dinitrogen monoxide. Oh, whoops, I didn't get that last part. Monoxide. So mono is 1. When you're talking about something, this will come up in the next one. Never mind. And let me read these out to you really quick too. Sorry, I know they're just listed here. Mono is 1, di is 2, tri 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8, nona 9, deca 10. As far as the A's at the end of these, most of the time they're going to stay there. But when it just doesn't sound right, like monooxide, that doesn't sound right? So we're going to go ahead and drop this last O. We're just going to pretend that that O is this O. Tetraoxide, it's tetroxide. So like you'll see that down here, but it would be tetroxide. Maybe it is spelled tetraoxide. Tetroxide. No, it is tetroxide. When they're right next to each other, it just sometimes it just doesn't sound right. I'm actually double checking. Nitrogen, yeah, tetroxide. So there is no A. That A is going to go ahead and get dropped right there. So tetroxide. But when you write it, it's just going to look kind of funny too. Right? That just looks a little weird right there. It'll become a little more intuitive as you keep naming stuff. But since I jumped all the way down to here, so again, we're going to use nitrogen. And then how many nitrogen do we have? 2. So we have dinitrogen tetroxide. Tetroxide. That just sounds super weird. So sticking with this, how would you name this guy right here? Give you a second to think about it. So remember nitrogen and then ox. oxide. So we have one nitrogen. So, and two oxygens. So I wanted to bring up a point. That's why I wrote this. This is not necessary. When you start with something that has one, you don't need to write in the mono. So mononitrogen dioxide would not be correct. It's just nitrogen dioxide. Because if you think about it, I'm telling you I have nitrogen dioxide. So you're like nitrogen oxide, two of them. I don't have to say mononitrogen dioxide because you automatically, when you heard nitrogen, would write the N. So we know that the N is present. But the second one will need the prefix, so monoxide or dioxide or whatever you're talking about in that case. So nitrogen again, and that is an enanthium. So we're talking about one, so monoxide, coming from the one. Again, I'm sorry about the quality of this video. I didn't prep any papers or anything, but I'm hoping it at least helps a little bit. Just like all of my videos, I just want, try to help you guys out a little bit, as much as I possibly can. You guys aren't asking very many questions. It's making me think you guys are chemistry gods or you're scared to talk to me. Please don't be scared to talk to me. I'm here to help you. So whenever I make worksheets, one of my favorite ones to put in for people to name is this compound. So let's break this down. When we first look at this, first thing that catches my eye is the fact that we have a metal here. So this is going to be an ionic compound, CMPD for compound. And then if you look as well, this is actually a polyatomic. So let's break this down a little bit further. Let's try to stick with the color scheme here. It's okay. So for sodium, or Na is going to be sodium, but Na carries a +1 charge if you look at the group that it's in. And I don't know if she dove this deep into it, but I want to make sure that I talk to you guys about it. Whereas over here, we have C2H3O2. Now, while you guys are still learning, you're going to need to, kind of go back and look these up. If we look at C2H3O2 under the anions on table 5.10 for common polyatomics, it's actually the first one listed. So C2H3O2 has a negative charge, and this is acetate. And then we know that's sodium. So the cool thing about naming polyatomics when they have, or naming compounds when they have polyatomics is, remember, it's cation plus anion, so sodium. And then we're talking about polyatomic here, so all we have to do is go acetate. We don't have to drop any endings or anything like that. We just need to make sure we're talking about the right thing. Just as a quick cliff note here, another way, there's a bunch of ways you can see this written. You can see it NaC2H3O2. And the reason I like to talk about this is because I call it the yummiest compound in the world. Or what compound can you get at Mexican restaurants? It's this one, sodium acetate, or nachos. Anyways, bad joke. But you can see it written this way. Acetate can also be written like this. And that's due to its structure, which you guys will learn more about soon, hopefully. But if you look at it, this tells you more about its structure than this does. Because if you look, you see CH3, so you can draw the CH3. That C is going to be bonded to this C, and then you have two O's left. You have to create an octet, So, and you have one negative charge. Again, this is a little bit further than she's covered, but it'll look like this. And then if you're looking at sodium acetate, you'll have a positive sodium there. So you can write sodium acetate this way as well. CH3COO in A, it's minus and plus. Those all mean the same thing. For now, I believe she would just focus on this one. Just know if you continue chemistry, that is going to be more common. Okay, so let me go ahead. Hopefully this kind of helped a little bit. Let me go ahead and write some examples. As I'm writing them, why don't you guys go ahead and try them? The ones in blue, you'll need to write the name. So blanks, then name. And then CMPD. And then the ones in pink will go with CMPD. Q will write the compound. And I will give you the name. So let's go back to the blue. Compounds. Let's go with that. So NH4,3PO4. This I'll save. I got one more thing. I have one more thing to talk about after this, but let's go Mg3P2. Let's go XEF6. Let's go AlOH3. And let's go, oh, this is a good one to bring up, LiH. Go ahead and work on those while I write out these over here. Let's go name-wise. Let's go calcium hypochlorite. Let's go potassium permanganate. Let's go stick with the potassium dichromate. Ammonium nitrate. And everybody's favorite, sodium cyanide. Alright, so give like 2 seconds so you can either pause or start writing stuff down, or pause and start writing stuff down. Alright, hopefully you've taken the time. Let's go ahead and do these. So right here, we have NH4 plus. We have 3 of them, but that's not a huge concern. That's just to balance this. And we have PO4 3 minus. So when you're naming something that has 2 polyatomics, You're literally just going to put the two names of them in order of cation, anion. And same thing here when you write your compounds, cat, and. And that's typical. That's how it should be. That example I showed you where they were switched, that has to do with more structure. But okay, so NH4 plus, what is that? What'd you get? Ammonium. And for PO4 3 minus, that is going to be phosphate. For this right here, so what is this? This is magnesium, so it's a metal, and phosphorus, so metal, non-metal, still ionic, and this is going to be magnesium. Remember, just name the cation, and then phosphide, IDE instead of phosphate, instead of phosphorus, it's phosphide. Alright, so we have, on the next one, we have xenon and fluorine. If we look, we follow that ladder, both of those compounds are to the right. So this is going to be a molecular compound. So we have no number for xenon, but we have a 6 for fluorine. No, by no number, I mean basically 1. So just xenon, and then the prefix for 6 is going to be hexa, and then just the root, or remember the root, FLUOR, and then the IDE for naming. So this right here, that was your root, this is your prefix, and then this is the IDE ending. This didn't need a prefix, so it's xenon hexafluoride. Alright, right here we have aluminum. And then, what was this one? This is HYDROXIDE, or hydroxide. So, remember, since it's a metal and non-metal, or in this case metal and polyatomic, we're just going to, since we're talking about a polyatomic, just using hydroxide at the ends. And for the cation, so it's aluminum hydroxide. So this is a tricky one right here. You see, you have lithium, and then you have hydrogen. You're like, huh? What? That doesn't make any sense. Why is the hydrogen there? Doesn't hydrogen normally carry a +1 charge? Well, yes, but it can also carry a -1 charge. Because if you think about it, this -1 charge is actually going to put it at a full 1s1 orbital, or 1s orbital. So that would put it at 1s2. So basically it would take this, it would take an electron from lithium, which would put lithium with the same configuration as helium. So both of these would have a 1s2 electron configuration. They would be isoelectronic. But getting back to it, so lithium, right, just like you would normally name it, and then hydra, like that's from hydrogen, and then hydride. So this is your root right here, It sounds really ridiculous when you say it, but so hydride is what it would be. Alright, jumping over here to going in reverse order, given the name and writing your compound. Let's go with red. So calcium, and then what is hypochlorite? Yes, perfect, ClO minus, right? Calcium carries what charge? You said 2+, you are right. So, one thing you can do to get these to line up is to switch the numbers. like basically turn the charges into subscripts. By that I mean Ca1, ClO2. And when you do that, you need to put parentheses around polyatomics. So we don't write ones. This is just for proof to show you what's going on here. So if we were to write calcium hypochlorite, it would be Ca parentheses ClO2, which, by the way, is used in pool supplies to chlorinate the water. Just thought I'd share that with you. On to the next one. So potassium, we have that for both of these. I'm going to go ahead and write it. What charge does potassium have? You said +1. You are correct. Because it's in group 1A, so it'll typically have a +1 charge. Permanganate, what is that? You are absolutely correct if you said this, MnO4-. So we'll use this little trick from up here. K plus MnO4-. I'm going to go ahead and swap the charges. So K1, MnO4, 1. Well, since they're both 1s, we can go ahead and just write K, MnO4. That tells me that there's 1 potassium and 1 permanganate. Alright, so potassium, like we said, was +1. Dichromate. So dichromate, di should tell you that there's 2 of these. And then from there, you really just need to remember that dichromate is Cr2O7, 2-. So to do this, to swap our charges, we are going to have this. I guess I should write it up here. K2 Cr2O7. Right, this comes from the dichromate, and then we need 2 potassiums to balance out the dichromate. Alright, let's go ahead and move down here to ammonium nitrate. Ammonium, if you said that is NH4+, you are absolutely correct. And if you said nitrate was NO3-, you are absolutely correct. This has a +1 and a -1, so we can just write it NH4, NO3. Typically when you're doing this stuff, you tend to combine compounds, like so N2H4O3. You can, I'm not even going to say, you probably should not do that. NH4, NO3, this tells me that this is ammonium and this is nitrate. If you put N2H4O3, there's so many ways that you can break that up. And it would just be impossible to tell what you have going on. So literally, you have your 2 names of your polyatomics right here. You can go ahead and just write the 2 polyatomics, make sure that the charges balance out to 0. Sodium cyanide. So sodium is Na+ as an ion, and then cyanide is Cn-. So again, we have a +1 charge and a -1 charge. Those are going to balance out to 0. So this is just going to be NaCN. There you go for that. Alright, I know this is already a 30-minute video, but there's one more thing that I realized when I was writing these. Transition metals. They can have more than 1 charge. So if we're talking about iron, iron typically does, oh god, was it iron 2 and iron 3? Yes, I think so. So you need to denote which is which. So if you see this compound right here, for some reason, yes, it's iron carbonate, which is like a really bad example. You probably won't run across that. But which iron is it? So to figure that out, we know that carbonate has a 2- charge, right? Most people are pretty comfortable with simple algebra. So what you can do is you can say Fe plus 2- is going to equal 0, right? So add the 2, Fe is going to equal 2 plus, right? So in naming this, we can say, it'll become like kind of second nature as you learn all your polyatomics. You'll know the charges automatically and be able to be like, hey, that's iron 2 carbonate. But yes, when you name these, you'll go iron 2 carbonate. The 2 in parentheses in Roman numerals lets the people know what charge you're talking about. When you're talking about, if you look on the periodic table, Ag, Cd, Zn, and then Al, Ga, In. So a neat little trick is go from aluminum and make a little staircase. Bam. Like this, right? So if you take these boxes, aluminum has a 3 plus charge, so do the 2 underneath it. Zinc only has a plus 2 charge, so 3, 2, 1. 3, 2, 1. You can think 3 of these with a 3 plus charge. Zinc and cadmium both have 2 plus charges, and then silver has a 1 plus charge. The reason I point that out is because zinc doesn't have other charges. Well, I'm assuming almost always, if not always, doesn't have other charges. Silver only has a plus 1 state. So, if we're naming AgNO3, that's just going to be, or I did it backwards, that's going to be silver nitrate. I guess, no, I didn't do that backwards, silver nitrate. Whereas if we're thinking of something like CuNO3 2, you have to denote that that's copper 2 nitrate. And I found that out because Cu plus 2 times nitrate has a -1 charge on it. -1 is equal to 0. So Cu minus 2 equals 0. Cu equals 2 plus. Whereas if we're talking about copper 1 nitrate, so just replacing the 1, that would be CuNO3. Right? So just be careful when you're talking about the transition metals. Those can have multiple charges, so you need to denote in parentheses in Roman numerals what those charges are. Let me give you one more. OS2, and this is osmium. I don't remember if she wanted you to know that charge, but OS2 SO4 7. How would you name that? Well, we know that sulfate has a 2 minus charge, so it's going to end in sulfate, right? Because we have a polyatomic there. So if we say 2 times OS plus 7 times -2 equals 0. 2 OS equals not equals. 2 OS minus 14 equals 0. I'm doing step by step just to clarify. Divide by 2, OS equals plus 7. So we would name this osmium. Yeah. Osmium VII, osmium 7 sulfate. Alright guys, well I hope that helps.